So you can go from any college in the States, do an exchange with Maryland.
Well, they have to approve it first. Like I had to do a whole process of approval for them to let me do it. But like I got it in the end, so
Sweet.
Couple more seconds.
Are you also doing like
Internet
No,
here is
I'm,
problematic.
I'm just here.
Open up a hotspot.
Getting years in the end. 67. You passed. Yeah, I passed.
Second. Oh. Hi, and here are everyone. Just a second, I'm having some technical difficulties. I need to restart my computer.
I think the only one who passed. Yeah. I don't know if anyone else passed.
In the meanwhile, I will say, especially to the new students, I record all sessions on YouTube Live, and they are open for you. I will add the links to the Lambda site later. The link is to my YouTube channel, and then you'll find this lecture by the number of the course, 89-112. I write the lectures on a Word document, which will also be available to you. And I think these are the main things for new students. I also teach them calculus, so I said all this already in calculus. My name is Erez Shaina. Work now. Now for you, full screen, and my video panel. Okay, I think I'm about done. And I'll open the Word file. That's fine. Okay. So welcome to the course Linear Algebra. When I introduce the course, it's a bit easier in calculus because in high school you learn a bit of calculus and you know about derivatives and integration. That's what I did. Linear algebra is a bit harder to explain because you don't know the basic language. It's kind of new. It's also something that some students like and some students do not like as much, because when it's completely new, it's brand new, so you can understand it from zero. And if someone has issues with calculus from high school, it sometimes lingers. It doesn't matter very much, but that's the main difference between the two courses, I think. And what I will say to you is this, and the main purpose of linear algebra is to study a linear function. It suggested linear algebra, which is true. That's what I wanted to say. Study linear functions. What are linear functions? We need to learn, right? You don't know it, and I'm well aware that you don't know it yet, right? But this is a purpose. And what are functions? You do know, right? Because you learn at the first semester the definition of a function, right?
Not all of us, some people that weren't in.
Yeah,
history.
right. Okay, but most of you, the other one can. It's just for the introduction, it's not that important. But in high school, functions usually mean real functions, meaning they get numbers, the input are numbers and the output are numbers. In discrete mathematics, you learn that the input can be any set and the output could be any set. The input could be humans and the output will be their pet cats, right? So the linear functions are between vector spaces, which means that the input are vectors and the output are vectors. Okay? Does anyone have a tissue? Functions? לא, אוי ואבוי לא. Just, yeah, I'll go to the bathroom real quick, sorry, because I can't speak.
You saw that Lev and Constantine started the first homework. Fucking morons.
I didn't know Java.
I did already said.
Wait,
Did they tell you what's happening to the people that didn't pass the first semester? In Intro to CS? Like, not doing object-oriented programming sounds like a blessing in disguise.
I think teachers don't know. I talked with Marina of our class.
Mhm.
And she said if you don't pass, you need to go to the international school and talk to them.
Okay.
The international school or the comp sci faculty?
I don't know. She said like not me. Like
Yeah, washing her hands and saying someone else has to
International
sit.
school and the comp sci faculty
Yeah,
both
yeah.
see the same thing. Little bit into
you can go both.
Sorry. It just, the cleaner lady just brought a new batch of fresh tissue. Okay, sorry. So we don't know what are linear functions yet, and we don't know what are vector spaces yet, and what are vectors, maybe a bit from high school, but not exactly what we need to know. But I like for you to see the overall picture, and I will remind you every now and again, that is what we are trying to study. And a bit more of introduction, what is a vector for the best of your recollection, for the best of your knowledge? What is a vector? Yes?
Oh, you want to
No, I'm just trying to remember.
It's a description of not really a movement that's too physical. You mean in math terms, computer science?
You can give me the physical explanation, it's fine for me.
A force and that has both magnitude and direction.
Magnitude and direction, that's what I was going for. So the geometrically, a vector is a pair of magnitude and direction. And the magnitude part is the quantity which is called a scalar or a number, and we will start with that. Okay, so the big picture is linear function vector spaces, but vector spaces use numbers, magnitudes, quantities, and we start with that. What are numbers? And I gave you a similar speech in calculus, which I will go through rather quickly and move on in a bit of a different direction. So we have the natural numbers, which are 1, 2, 3, and so forth. Then we have the integer numbers, 0, plus minus 1, plus minus 2, and so forth. Then we have the rational numbers, all of the fractions, fractions, p over n, where p is an integer number and n is a natural number. And then we have the real numbers, which I didn't give you a very good explanation of, but I said all of the decimal fractions, including infinite number of digits. The real numbers are more important for calculus, and I told you there is a square root of 2 there, and we need it. In linear algebra, it's less important. But now I will ask, are these all the numbers? Which is a false question, but fine. But what is the next set? What is the next set over the real numbers?
Fake number.
It's not a fake number, the imaginary, the complex numbers, right? And the real numbers are parts of the complex numbers, which we will study first. But in order to understand these new numbers, we need to understand what is a number. Okay, so I think I'm opening for a second to see what I wrote about it in calculus. I think we said it was a quantity, right? Let's just check it for a second. And I'm sorry for whoever is not in calculus. I won't always connect the two things, but that's the introduction part. So I don't want to be too repetitive. What are numbers? Yeah, a way to measure different quantities, right? So that's the same thing I want to say now. A way to measure a quantity. Okay. And my question is this: are the numbers we mentioned above the only numbers there are? And obviously I said, well, if I would ask, are the natural numbers the only numbers? No, because they're the integer numbers, and then the rational numbers, and the real numbers, and the complex number. What I'm asking is this the only tree of numbers. It's the only way that numbers goes. Is another question I will ask may help. Is it always true that 1 + 1 = 2?
No.
Why not?
Because,
No, you go first this time.
are you sure?
Yes, for sure.
Different numbering systems or different ways to represent numbers is one reason. But
But
like,
why are there, that's the question, are there different set of numbers and why? That's exactly what I'm asking. Because we said numbers measure quantity. One is a quantity. Isn't it always true that if you have one quantity and another one quantity, don't you always have two quantities?
No, because
Why?
when you, for example, let's say you're talking about water. Yeah, you have a drop of water and another drop of water. When you
It's
add
funny
two drops
because
of
the
water
student
together, you
told
have
me that
still one drop of
yesterday.
water.
But that's a pun rather than a mathematical observation because
Well, technically, but it technically
because
is.
no I disagree because the drop is not well defined and that's the problem here. That's not what I'm meaning, and in any case it's not what I mean, like normal quantities I think. And I will ask you the following question. If now the time is, let's see, the time 1, right? What? No, 1 is not good for me. Say the time now is 7, right? What will be the time in 8 hours? It won't be 15, right? It will be 3. So in this system, 7 + 8 = 3. 15 because 15 p.m., right? It's 3 p.m., it's 15. But if I add to 15 another 8 hours, I will get to 11, right? No, it's still in the same day. I wanted to go over, whatever. So you see the different quantities could have different meanings and even different operations, right?
Galois fields, that's the answer.
Yeah, I'm not going all the way there, right? Another question which I like, if you press the elevator one time and then another, 1 + 1, what does it equal?
1.
So it depends on the elevator, but right, on old elevator, 1 + 1 is 1. If you pressed, then you pressed again, you get to the same result, the same quantity, right? If it's a new elevator in a modern elevator, what is 1 + 1?
0.
0, right? And that's for computer science guys, because that's the binary field that you actually work with all the time, right? So you have different ways to measure quantities and calculate the operations between them. And then the next, and why do I say that? Because I'm about to present to you the complex numbers, and you first need to be able to accept that there could be different numbers, different quantities than that you are used to. Do they complex numbers measure any quantity? Would you say I is a quantity? I would say yes. Many lecturers would say no, but I will say yes. And I will show you, it's a bit of a shara, curricular, I don't know. I will show you the quantity of complex numbers. It's not very important for the course because even myself, I used to say, okay, it doesn't measure quantity, but algebraically it's a number, which we'll speak about what does it mean to be a number, right? But it also does measure a quantity. We'll speak about it a bit. But the main thing, we're in linear algebra, So what defines a number? And I will say in algebra, the main obsession
Relative obsession.
are operations, addition, multiplication, and their properties. In general, if someone says what's the difference between algebra and calculus or geometry, geometry deals with the shapes, calculus deals with the functions and their slopes and limits, whatever. Algebra is all about the operations and their properties. So I will give the algebraic definition of a number. The actual definition will be a field, right? But the elements within the field are called scalars or numbers, okay? And that's the way we will go because the course is linear algebra. When Euclid spoke about numbers, he thought on the size of segments, right? Because he was very, very into geometry. We are looking at things much more algebraically. So we'll define it already. Yeah, let's define it. Definition. A field is a set F of elements which we will call scalars or numbers, usually scalars, along with addition and multiplication operations. So I get the elements and I get the think of it as a huge list, possibly infinite list of for every two elements, what is the addition of these two elements and what is the multiplication of these two elements, right? So all of this is given. So one can say, okay, so my car keys and my wallet are a field. How much is car keys plus wallet? Say it's a phone, right? Are these numbers? Possibly. If the following 7 properties hold, right? It's not just random names and random operations. There are properties which you know them, all of them, you know them, and you know that they hold true for the numbers that you are used to work with. But we say that any number system that holds these properties is called a field, and it's okay to work with it in linear algebra. What does it mean, okay? For equations, linear equations, and vector spaces and whatnot, these scalars, I can use them to prove my theorems. You will see that as the course develops.
So
I didn't finish.
yeah, no, just asking
Okay.
about you mean that like every number is in the field, like every possible combination of every number? That's
No, the field is a set of elements. It could be my car keys, my phone, and my wallet. It could be that this is the set, but I need to define to you what are the operations, and then I need the 7 following properties to hold. If they do not hold, it's not a field.
Okay.
Okay, and I will show example of when it holds and when it doesn't hold. Okay. Such that such that operation such that the following 7 properties hold. It's not what I meant. Hold. So the first one, for every A and B elements of the field, it could be even the same number, right? Even if A equals B, it is true that A plus B is a number, and also A times B is a number. Okay, so the first property I wish to have, the sum of two quantities is a quantity. The multiplication of two quantities is a quantity, right? Agreed? If I would say that the field is my car keys and my wallet, and the addition of car keys and wallet is the phone, and it's not a member of F, then it's not a field. I'm not accepting that as a field. The first requirement is that the sum of two numbers is a number and the multiplication of two numbers is a number. Agreed? Second, for all A and B in the field, every two elements, A plus B equals B plus A, and also A times B equals B times A. Commutativity. Agreed?
In which cases is this not true? Like, isn't commutativity part of the definition of multiplication?
No,
No.
no, because addition and multiplication means nothing. If I can decide that phone times car keys is wallet, but car keys times phone is phone, then I can decide that, but I would say the system that I invented is not a field. And there are elements, we'll see them. We'll see such elements. Matrices does not do not commute on multiplication. That's why matrices will not be a field. They won't be scalars or numbers in that case. So there are things that are called even multiplication, which are not commutative.
I was gonna point out.
Yes. Okay. Next, and the reason that you think it's obvious is because you know these properties hold for the numbers you know. But now I'm trying to define what constitutes a number, right? So I wish addition multiplication require, not switch, to hold this property. And next is associative law. For all A, B, and C, every three elements, not necessarily different, of the field, A plus B plus C equals A plus B plus C, and also for all A, B, C, I move the line further just because I don't have room in the upper line. For every three elements, A times B times C equals A times B times C. Agreed? Next, for neutral elements. There exists this.
No, without this. Yeah.
There exists a member which will be called the zero of the field in F, such that for all A in F, A plus 0 is A. And there exists a number one of the field such that for all A in the field, A times 1 equals A. And another requirement here is, and 0 is not 1. It's not obvious by the other requirements, it doesn't fall from them. We need to require
They are different.
that they are different. So because otherwise there could be a field with only one element, phone. Phone times phone is phone. Phone plus phone is phone. It will all the other properties will hold apart from the requirements that says the natural elements, the neutral numbers should be different from one another. Next. 5. For all A in F, for every number, there exists an opposite number, which we call minus A, such that what, or negative A, what is the connection between A and negative A?
What is the other? Oh, no, it's
A plus negative A equals 0. Does negative A
Zero.
has to be different than A? Could A and negative A be the same number?
yeah, probably.
0 for sure, right?
In-
But let's go back for the elevator for a second. The modern elevator. If I press 1 time, what will be the operation that will cancel out me pressing another press? In the modern elevator or in the binary field, -1 equals 1. It's the same number. 1 plus 1 equals 0. In the regular numbers, only 0 has this property, but in other number systems, yes.
Can we say also that for a trigonometric function, just like a sine of 180 and 180 is 360, but it's also 0, or
You could, it's something similar. Every modulo action has the same properties. You could, yeah, yes.
Should the notation not be an inverse instead of a negative? Like
No, inverse is not a negative. Inverse is inverse. It's the
That's the
stick
next-
property.
that's the next thing, yeah.
Yeah, 6. There are only 7, so we're nearing the end. For all A, does every number has an inverse?
No.
Who doesn't have an inverse? 0. So for every number which isn't 0, there exists an inverse number such that
A times the
A
inverse of
times A inverse equals 1.
I see the top one is for addition.
Yeah, exactly.
The sixth is the-
And
technically it could be the same.
I will point out this is the first distinction between addition and multiplication. All of the properties thus far were exactly the same. This is the first distinction. All numbers has an opposite number, but not all numbers have an inverse number. The 0, the neutral number for addition does not have an inverse. That's maybe the only definition between addition and multiplication. It's a small one, but it's important. And what is the 7th property? I will give you a hint. I said that the 6th property distinct between the 5th and the 6th property give distinction between the two operations. What gives a connection, a link between the two operations?
That you can make multiplication from an amount of summations or,
No, but that's just for natural numbers. It's not true in general, right?
okay,
Who has an idea? An elementary school law, which you all know, and that will be the seventh property that contains both addition and multiplication in a
Addition-
formula.
Addition is multiplication, like.
No, that's what I said. That's
That's
for the
not-
natural number. It's not true in general.
distribution?
Distribution law, exactly. For all A, B, C in the field, A times B plus C equals AB plus AC. Okay. So these, oh, wow, I didn't save that's far. That's important. Just a second. Save as from and Shpa, Vet, linear, board. This directory will be available to you using the Lambda. Linear algebra. Okay. So these are the 7 properties of the field. And one thing I did not mention, which is most important to the students, is when do we take a break? So in general, since linear algebra is 3 academic hours, it's 2.5 actual hours, and it's 2 hours and a quarter. So we add a quarter, 15 minutes of a break. I take them usually about after about an hour or an hour and a quarter, and then we finish the lesson. So that will be it's dependent on the point in the material that I am, but between 2 and 2:15 we will take a 15-minute break. Okay, and we finish at 3:30, I think, right? And then at 4 we study. That's the next place. That's calculus. So we have a definition, and we have to have examples in order to start to understand it. So the first example would be, let's define our supposed field to be A, B, and C. It could be a field of numbers, even though A is not usually a name of a number, it could be. What should I define and give you on top of the name of the elements? What else should I provide you? What's
The results of the operation?
the operations exactly? And then I will define to you given the set and given the operations A plus B equals C, A plus C equals B, and B plus C equals A, and so forth. When I say so forth, you can't understand what are the results other than that, but I mean, assume that there is a definition for all of the other operations. Could this be a field? Just given this partial information. I didn't give you all the data because I didn't give you all the operations. That's a hint for the answer, right? I told you these 3 operations are true. Could this be a field?
No.
Why not?
You don't have multiplication in that school.
No, but there is multiplication. I just didn't tell you the results. There is,
But we need
it's
to know-
it's in the 3 dots.
But we need to know the result in order to prove whether it's a field.
I
Not
disagree.
necessarily.
I disagree. But
No?
assume that I just didn't give you all the other operations that exist. I could write a plus b, a times c equals and question mark. They are all here. They are defined. That's not the question. But another question: is there, if you like, is there a way to complete the operation so that will be a field? Okay, if you prefer this articulation of the
We
question.
don't have a zero, I think.
There is no neutral addition number. Okay, no number. There is no zero of the field. And how do you know there is no zero? Is it because none of the elements were named zero? No, that doesn't matter at all. Why do you know that there is no zero?
Because we'll have things like a plus b equals a.
Exactly. If a was zero, if this was, if this was a field and a was the zero, then a plus b should have been b. It's not. Not. Similarly, no other element of the field could. I don't like that I'm saying the field because it's not a field. No other element of F, the contender,
Of the set, maybe?
could be, yeah, could be the zero. Okay, so I am able to invent such a set and such operations. So such operations, I'm allowed, but I'm not allowed to say this is a field. I'm not allowed to use these as the scholars with which we'll build our vectors later in the course. Okay, agreed? Definition. Definition, what we mind? Yeah, okay. Given a natural number n, and I'm emphasizing it's not zero. N. We define
Depends.
and given another number k, it could be an integer number, but I will say a natural number. I think it's enough for me. We will define k mod n to be the remainder when dividing k by n. For instance, what is 16 modulo 9? So if you divide 16 by 9, how many times 9 enters into 16? Once. And what is the remainder? 7. Agree? Do you know this or not? It's important because you might have seen it in computer science, right? You use the percentage percent symbol to calculate modulo. Let's do a couple of more ones because it's important. Sometimes students who don't understand say, let's see where he goes with that. But you need to understand the operation here in order to understand what I will say next. So again, another example. What is 17 modulo 5? How many times does 5 fits into 17? 3 times, and that's 15. And what is the remainder? 2. Agreed? Okay. So now let's look at the n, which is the set of all the remainders. 0, 1, 2, it's the ring of remainders, the formal name. And when I give you the elements, is it enough in order to say if it's a field or not? No. What do I need to give you on top of the elements? The operation. And define that the addition of 2 elements, A and B, is A plus B modulo n, meaning you're doing regular addition and then you divide by n and are left only with the remainder. For instance, example, if we look at Z12, let's take the 2 numbers we did before. They were 8 and 7, I think, right? So how much is 8 plus 7? No.
13, 15, sorry.
Also no. 3.
Right.
Right? Because the regular addition of 8 and 7 is 15, and we take the remainder when dividing by 12.
Wait, what is? Oh, okay, I see. A plus B should be in brackets. Right?
Yeah, I agree. Okay, you do regular addition and then modulo n, and that's your result. Okay, agreed? How much is 6 times 5 in this structure of the hours of the time, right, of the day? What is 6 times 5?
6.
Basically what I'm asking, if I don't know, doing laundry takes me 5 hours and I'm doing 6 loads, what will the clock show after I finish all the loads, right? 6 times 5. How many hours will pass in the clock? So what is the answer?
The hours is it's 30 and then you're sorry, 6 hours.
6 hours, right? Because 6 times 5 is 30. We divide by 12. So 12 fits twice into 30, that's 24. And what is the remainder? 6. Yes.
But we defined for addition, the fact that I do it again for.
Oh, you're absolutely correct. I forgot to write the same thing for multiplication. And multiplication of A and B is. You're right. Okay. So both addition and multiplication are defined by this action. So look at this. What does this tells you? If 6 times 5 is 6,
6 times 4.
that's not what I'm asking. What does it mean? What does it tell you about 5?
5 is 0. No,
Not 0. It's maybe the 1. So maybe 5 is the one of this supposed field, right? Because when I multiplied some number by 5, I got the same number, right? It behaves like the 1. But it is not true. Actually, it is not a field. The numbers on the clock are not a field. And how can I know it's not a field? I need to show that not all properties hold. Quickly, I will tell you that the first 3 holds with no problem. Also, the second 0 is the 0 and 1 is the 1, because also 1 times 6 is 6, right?
But 5 doesn't.
5 does.
5 does?
5 does. Yeah.
Why? But if
For every number, take 12 minus that number. Right?
because it's
7
negative.
plus
Okay.
5 is 0 because it's 12. And 7 also holds. The only problem is 6. Not all numbers have an inverse. And how can I know for sure that there isn't an inverse? Luckily, it's a finite set of numbers. I will try all of them for a certain number, and I show you that none of them invert it. So look, take 2. We will see that 2 does not have an inverse. So 2 times 0 is 0. 2 times 1 is 2. 2 times 3, 6. 2 times 4, how much is that? 8. 2 times, oh, it gets interesting. No. It's 10, now it gets interesting. 2 times 6,
0.
0. Why? 2 times 6 in regular multiplication is 12. And when you divide by 12, the remainder is 0. What is 2 times 7?
Oh, 2.
It's 2. And 2 times 8 is 4, and 2, I add 2 each time. And 2 times 10 is 6.
This is
And-
all in the field of mod
Yeah,
12.
but it's not a field, but yeah.
Uh,
On the set I defined with the operation I defined, which is not a field. It's called a ring. It's the ring of remainders.
sorry, you skipped 9 on purpose.
No, sorry.
And also,
And 2.
So
the negative
wait,
number.
so yeah, so 2, 4, this is 6, right?
You
Yeah.
skipped out 2 times 2 as well.
Oh, right. I don't know why. 2 times 2 is 4. Thank you. And 2 times 10 is 8. I should have picked a lower number, but that's the clock. That's why I used 12. And 2 times 11 is 10. And the result was never 1. So there is no inverse. I needed some number to be the inverse. There is no inverse.
Sorry, for modular fields, or how do you call this?
Rings.
Rings. For rings also, when you're talking about integers, are the negative numbers also there or not?
So what is a negative number? What is mine and the negative 3? So it is the number when you add to 3, when it adds to 3, it becomes 0, it's 9. So it's there. Negative 3 is there, it's just called 9. Because 9 plus 3 is 0, right? That's the definition of the negative number, is the number when you add, you get 0. So there are negative numbers there, but unlike the regular numbers, they are not different than the other number, right?
So not necessarily, I mean, probably the actual definition is way more complex and we'll talk about it later, but like it's not necessarily that you add a negative number to a positive number and the result is less.
Yes, it's not an ordered field. There is it's not an ordered field. That's true. And by the way, for general knowledge, all of encryption is based on this fact that when you do the action a few times, you're not always going to the same direction. That is why to invert the encryption is so hard. And that's why encryption goes over the modular field. Okay? Or ring. Okay. And for your general knowledge, I will not prove it. For general knowledge, Z and is a field if and only if someone cares to guess. What is the requirement about n which will make it a field? 12 for 12 it wasn't a field.
It's all.
What? Not all, no.
It's one.
No, for one it's not. For one it's definitely not, because
have to be defined.
module one there is only 0 and that couldn't be a field. It's too small. There has to be at least 2 elements.
So the reason why this failed was because the multiplication between
The inverse failed.
there's no inverse.
Yeah.
But for there to be an inverse, it has to be fractional, no? Or
No.
Mm,
Only if and only if n is primary. Primary, Rishoni.
prime. with-
Prime. Sorry.
Yeah, prime.
Prime. It's another thing in mathematics, but another thing.
Yeah.
Sorry, it's a prime number, Rishoni. Okay, and for instance, the most for instance, Z2 which consists of 0 and 1 is the binary field, but Z5 is also a field. And let's work with it for a second. So what are the elements in Z5? They're supposed to be the remainders. 0, 1, 2, 3, 4. And excuse me, what's your name?
Thomas.
Thomas. So Thomas is asking, how could 0, 1, 2, 3, and 4 be a field? There are no opposite numbers and there are no inverses, but you will be wrong. There are opposite numbers here and there are inverses. What is the opposite number of 1? But there is no
Five.
-1. Your
Five.
answer has to be one of the elements written here. You can't say just -1. In regular numbers, yes, 1 and -1 are 2 numbers. But here, these are all the elements. These are all the numbers here. Like in the binary field, the only numbers are 0 and 1, on and off. And what is the inverse of on or 1? Again on, right? Because 1 plus 1 is 0. The same goes here. What is the opposite of 1? Think
One.
about well, it's not an elevator, but a button which rotates between different מצבים. States, thank you, of, I don't know, a lamp, like different values of power, right? Levels of power. So if you press once, how many times will I have to press? I can't unpress, right? I can't pull the button out. How many times will I press to get back to 0 after I pressed once? No, here, no, I'm saying, assume you have 5 states, off and 4 different levels. So I pressed 1, I'm at 1, pressing again 2, pressing again 3, pressing again 4, pressing for the fourth time, I'm back to zero. The opposite of one, the negative one, is 4. And why is it true and why does it follows from what we said? Look at 5. The requirement is for every number there exists some other number, or maybe the same number, there exists a number such that what? Their sum is 0. And in Z5, how much is 1 plus 4? No, 0. Yeah, 0. Because you need to take the remainder when dividing by 5. So 1 plus 4 is 0. And think about the states. If I press 4 times more, I'm going back to 0. There is no state 5, but I'm going back to 0. Agreed?
This is not what was the problem last time, right? Not
No, yeah, because in general, the negative number is n minus the number.
Okay.
So that always works.
yeah.
Okay, the inverse is the main problem. And think about it like this, and it's starting to be linear algebra. Can you solve the equation 3 times x equals I don't know 4 in Z5? In Z5. And think about it for a second. If I ask you 3 times x equals 4 in regular numbers, in the real numbers, you say no problem, x is 4/3, right? But here 4/3 is not a number. You have to answer either 0, 1, 2, 3, or 4.
Can I think about it like how many times we need to push the button multiplied by 3 to be 4? So
Yeah.
we have 1. From
No, from 1, but not from 1. Here you
okay.
need to start with 0.
Okay,
It's-
so
Are
it's
we-
But I'm going in another direction.
Are we supposed to work with
I
this?
want to divide by 3.
yeah.
Agreed? What is division? It's multiplication by the inverse. I wish to find a number a such that a times 3 times x will equal, x. That's what I wish. I wish to find a number a such that a times 3 times x will equals x, because that's the ability to divide, right? So I need a times 3 to be 1. So just a second. So a has to be the inverse of 3. And then, so if a is the inverse, then a times 3, a times 3 is 1. And the question is whether it's possible. In Z12, for the number 2, that was impossible, right? Because I took 2, I multiplied it by all of the elements of the ring of Z12, and I never got 1. What I'm claiming without proof is that when the n is primary, all of the numbers which are not 0 have an inverse number, definitely. Okay, I won't prove it, but it's a nice thing for anyone who's interested, but it's not the main reason for the main subject of this course. The only reason, to be honest, that I'm talking about the modular field is for you to understand that there could be different numbers than the ones you know, and based on that, I could you would accept me defining the complex numbers, which are different than what you know. That's my main agenda here, to be honest. But I'm not inventing stuff. These are true systems, right? But I need you to understand that there could be different systems of numbering, and I will present to you the complex one, okay? So what times 3 equals 1? It's easy enough because I have only 4 numbers, right? 1 times 3 is 3. 2 times 3,
It's one.
it's 1, right? Why? Because 2 times 3 is 6. And when we divide by 5, the remainder is 1. So we notice that 2 times 3 equals 1. And look how that will solve the equation. Because I have 3 times x equals 4. So we will multiply by 2. And then on the left side, we get x. And on the right side, how much is 2 times 4? Yes, 3.
Oh.
8, the modulo 5 is 3.
Yeah.
And we solve the equation. Let's make sure it works. Let's see if it works. Indeed, how much is 3 times 3?
9, the modulo 5 is 4.
4.
Yeah.
So we were able to solve an equation in this new number system. It's hard for us because we are not used to it. We are used to the regular numbers. But all of linear algebra, which will contain solving of equations, will work over every field of numbers. The proofs, the theorems will work over every field of numbers. Technically, it could be harder for us because we are not used to it, but theoretically, we'll always get the same thing because every number has an inverse. So given a field, because it's one of the properties we required. So in every field, I could do this theoretically, even if I don't know technically how to find the inverse, it exists. Okay, understand?
Yeah.
Any questions so far?
Uh,
Yes, Thomas.
we now use brute force. We are going to learn a different way of doing this, or is it like usually
There
like
is a different way in logarithmic complexity. You won't learn it because it's not the subject of this course. But like I said, when you learn encryption, and you probably learn it RSA sometimes, then you will learn how to find the inverse. For us, it doesn't matter at all. We're taking a break in a second, and then I probably never get back to the modular fields because it's not the main thing in this course. I will go to the complex fields, which is
way more fun?
which is what we do need to learn. So let's take a break until 2:30. Yeah, no, sockets around.
Where are you going?
It says
חושב שאנחנו צריכים באמת להבין את זה לעניין, זה סתם היה לכיף, וזה כן, זה כאילו מעניין פיצוצים.
שוב, אז מה זה להבין? הרמה שעשינו, אתה צריך להבין.
לא, אבל כאילו 7 חוקים וזה, ולהיכנס לעומק.
זה משהו אחר, 7 חוקים כן חשוב, אמרתי שאני רק לא אזכיר את המודולו, 7 חוקים כן צריך לדעת.
אוקיי.
אל תדאג, זה לא, אם הפחד זה מלשונן, זה לא...
לא, זה פשוט...
אבל להבין בוודאי, זה האלגברה לינארית, אנחנו נתעסק הרבה עם החוקים, ויהיה גרוע יותר בהמשך. אבל כן זה הקדמה, כי אלה החוקים של שדה, ואחר כך יהיה חוקים של מרחב וקטורי. ומרחב וקטורי, כמו שאמרתי, זה כבר הנושא של הקורס. אז כאילו זה מעין פתיח כזה שמכניס אותך.
יכול לחזור שנייה לחוקים, כי אני, מה שבאמת, שאלה זה כל האקטיב הזה.
אז זה אני חושב כי אתה לא למדת בדידה האמת, בגלל זה אף אחד אחר לא התלונן חוץ ממך.
אני עכשיו מבין,
אז זה, כן, כן. אבל אל תפחד מזה. כאילו, אני מבין, בוודאי שזה יפחיד מישהו שלא למד, אבל בגלל זה הקראתי במילים כל הזמן מה אני אומר. הסימן הזה אומר לכל, והסימן הזה אומר קיים. והסימן הזה קיים, וזה אומר וגם.
וגם, כן, זה וגם, או הפוך זה, או, אבל מה זה כאילו, לא,
זה?
כן.
זה לא חשבתי שאתה לא יודע, זה שייך. חלק מזה.
זה, אוקיי, זה
כן.
היום למדנו שייך.
כן, לא, ברור שזה כיתוב לך קצת, אבל תאמין לי שזה יעבור לך מהר.
סבבה.
כאילו כאילו, אף אחד לא שאל, אני חושב, כי הרוב מכירים, ואז
אני
אף אחד
מאמין
אחר
שרוב
לא
אז-
שאל, כי אף אחד אחר לא שאל. אבל כאילו זה באמת,
הספציפיקציה.
זה חבלי לידה קצרים כאלה, כאילו להביא את
אוקיי.
זה, זה לא העיקר. העיקר שאתה מבין זה חוק החילוף,
אוקיי.
סגירות, אסוציאטיביות,
אוקיי,
ואנחנו
אוקיי.
נזכיר אותם עוד קצת כשאני אדבר על המספרים
סבבה.
המורכבים, אז אני אחזור על תכונות ואגיד, הנה אתם רואים,
כן.
המספרים המורכבים באמת מקיימים את התכונות.
אוקיי. והשיעור הולך עד 3, נכון?
עד 3.5.
עד 3:30. כי זה מסיים בעצם.
כן,
כאילו,
זה 2.25 ועוד
אוקיי.
רבע זה 2.5
ואז יש
מההתחלה.
לנו באמת,
ו4,
אני חייב לרוץ למעונות לקחת מתן.
יש חצי שעה.
go to any class and you don't go into any class in university, you obviously won't pass. But I mean, like, how you did in English literature has nothing to do with how well you do in computer science.
No,
So, like,
exactly. But how I did in English maths and English further math, which I did both of, should have mattered, and it didn't at all.
because our program is
So
like
let's begin. We'll talk about the
we'll fight
problems
about it later.
later.
We
We
have
won't solve them. We
we
talk
have
about
3
them
more hours.
constantly for years, but yeah. But it's okay to talk. So we're back. And my next agenda is to define the complex numbers. Next, we wish to define the complex numbers and show that it is a field. I'm saying show and not prove. It's because I won't go through all the steps. One can prove that it's a field, but I will show some of the steps. So how many of you have seen the complex number before? Some, not all. And I will start from the base, from 0, but I will go quite fast. And for the first part, it won't look like the complex numbers you know, but quite early it will go back to the notions and notations that you already know. Okay? So first of all, in order to define a field, one should choose the elements and the operations. Okay? The elements of the complex numbers set are the points on the plane. So see, it's all of the pairs A, B, such that A and B are real numbers. So that's the first thing you need to, I don't know, accept the elements here. The numbers are here are points on the plane. I'll show you for, I don't know, visualization purposes. So this is the plane. So 1, 2, that's a number. That's a complex number. And also -3, 0, that's a complex number. Any point on the plane, any pair of A, B, where A, B are real numbers, is a complex number. It's hard to accept that the number is a point on the plane, but that's why I did all the introduction to convince you that I don't have to convince you that every element is naturally a number or a quantity. I assure you it does measure some quantity, even though you can't see it right now, but it doesn't even matter. These are the elements. What do I need to do next?
Operations.
Define the operations, because if these are numbers, I should be able to sum them up, add them to each other, and I also need to be able to multiply them. And it's not naturally obvious how, because I don't really even understand why are these quantities, much less how to multiply them and how to sum them up, add them to each other. And the addition is quite natural and intuitive. The multiplication is not at all. Okay, but I will define them in a minute. Any questions so far?
I don't know if you were about to say this, but this A is the real part and B is the imaginary part.
That will be later decided. Now I wish to build a field. I wish to point out a certain number, which I will call I, and prove that I squared equals -1.
Yeah.
Okay, but for now it's we'll see. So these are the numbers, and we define that the sum, the addition of A, B, and C, D, two numbers, will be A plus C, B plus D. Just by define the addition as such, let's look at the properties I wish would hold. Is the addition of two complex numbers a complex number? Yeah, look at it. I added up 2 points on the plane, and the result was a point on the plane. So the addition of two complex numbers is a complex number. How about commutativity? Do they commute? Yes, why? Because the addition here is the addition of two real numbers, and the addition of real numbers is commutative. So it commutes. How about associative law, the third law, A plus B plus C? It holds, I won't show it, it's not very hard. How about the neutral number? Is there a zero in this field? Which number? 0, 0, look. A, B plus 0, 0 is A, B, always. So I have a neutral addition for addition number. And how about opposite, negative numbers?
Yes.
For AB, which is the opposite number, the negative number? Minus A minus B. So for addition, everything holds. I didn't go through distribution law, the seventh one yet. Why? Because I didn't define the multiplication yet. But everything which is just addition holds perfectly. Okay? So this I wish to write. This is the zero of the complex field. This is 0, C. Okay. Now, and that's a note. I will move it down. Now let's define the multiplication. So it will look quite odd. Later we will see why does it make sense and how come and how someone thought about it. But for now, I just give you, this is the formula. This is what we define. So it's the left times the left, so A times C, minus the right element times the right element. So it A is times C minus B times D, comma, the outward ones, AD, plus the inner ones, outer and inner, BC. So that's the definition of the multiplication. So just look at this part. I defined the elements point on the plane. I defined the addition of two elements, and I defined the multiplication of two elements. It's not obvious why did I use such a convoluted formula. I will give you a few answers, some of them better than others. Well, I mean, two answers, both of them good for me. But for now, that's just the definition. And the question is, where are these elements with these two operations constitute a field? And the question is actually whether the 7 properties hold. And quick answer, yes. Okay, but it's not that easy to see why they hold. I mean, yes, Thomas.
If you know how complex numbers work,
you don't know how complex number
so
works.
assuming
This is the first time you see complex numbers.
I have never seen them in my life, but assuming that I did, this makes sense.
It makes sense only because you are already familiar with I and complex numbers. It doesn't make sense.
Okay, sure.
Be honest, it
No,
doesn't
I
make
mean,
sense.
I mean, I started thinking of why in the hell would someone do this, and then I thought that.
No, you will get the answer by the end of I think of today even, of where did this formula come from. No one started like this. It happens many times in math. Someone invents
We start from
something,
the
he
end.
does it, and I say that's what I need. He sees it in the end, and I will show you like I invented it. It's not true, right? But that's the best way to do it in the most exact way, and I don't know.
We don't deal with imaginary numbers in Infi 1.
With a complex number?
Yeah,
No, infi is just the real numbers, and yeah, there is a course on calculus over the complex numbers, not in computer science, so
great.
you can relax, take a breather.
Yeah.
Okay, so let's do a few examples, just seeing that we are able to calculate these operations on different numbers. So here I put 1, 2, and -3 and 0. So first let's add them up. 1, 2 plus -3 and 0. What is the addition of these two numbers by the formula above?
There's -2.
-2 and 2. Agreed? Let's sum them up here, a plus b. Let's hear -2 and 2. Does that make sense?
Yep.
Doubtfully, I know.
It's somewhere over
It
there.
looks like addition of vectors, actually.
Yeah.
But still, because we don't understand it as quantity, when I say 3 apple plus 4 apples, I can see 7 apple visually quite easily because I understand the quantities, right? Here I don't understand the quantities, but there are, and I will show you later. But I don't think it makes sense. I don't know. Okay, but it doesn't matter, right? It has, that's just a calculation. I insert the numbers into the formula and find out what's going on. Now the multiplication is even more horrible. What is 1, 2 times -3, 0? So
-3 minus.
yeah, so it's the left times the left. So it's 1 times -3, it's -3. Minus the right times the right. So 2 times 0, it's 0. Okay? Comma. Now, the multiplication of the outer one, the product of the outer one, so it's 1 times 0 is 0, plus, which will be minus, because it's plus the product of the inner one. So 2 times -3 is -6, so it's -6. So the answer is -3, -6. Let's put that up. -3, -6. Where is it? Here. Does that make sense? That this number times this number equals this number?
Usually that.
Doubtfully, right? I hope I didn't do a calculation error because it looks too horrible. Let me think about it for a second. Oh, it does make sense for me. Sorry. It will make sense to you as well later because we will learn the geometric meaning, the geometric meaning of or visualization of this product, but knowing nothing else, it's just plain weird. Okay, but it's important for you to understand that we are allowed to do it. Just as you program a computer program, you write a computer program, the computer will do as you say. It doesn't search for meaning. So think about it as a function in Python or whatever, which takes 4 variables and present 2. Okay, the left one will be this and the right one will be this. Okay, so that's the definition. And now, is there a unit one of the field? The natural number for multiplication is sometimes called a unit. So is there a number which is neutral for multiplication. AB times what?
What is a unit?
Like,
So, the one of the field.
like 1, 1.
One of the field.
Field, the neutral number for multiplication. So I'm asking for a number. What are the question marks should be so that the result will be AB, right? If it's a field, there's supposed to be some number that when you multiply any number by 1, you will get, so I wrote F, but it's supposed to be the complex, right? Double C. Okay, I wish to find
1, 0.
the units, the neutral number for multiplication. Okay, so usually the first guess is 1, 1, which does not work. 1, 0 actually does work. That's true. AB times 1, 1. Let's try that first to see why it doesn't work. What does it equal to? What
A minus B.
A times 1 is A minus B times 1 is A minus B, and we already see it doesn't have to be A, right? If B is different than 0, then it doesn't work. Okay, and here you'll get A plus B. But that's not good. But if you multiply AB by 1, 0, left times the left is A times 1 minus the right times the right, it's B times 0. Right? You see, I'm simply substituting it into this formula to calculate the product, right? And then the outer ones, A times 0 plus the inner ones, B times 1. And what did we end up with?
AB.
AB. It works. Okay. So we seemingly have a unit, the one of the field. A number, when you multiply anything with it, you stay with AB. Okay. And distribution holds, I won't show you, and all of the most other properties hold. It's not very hard. The main one is 6, the inverse one, which we'll deal with for sometimes. The other ones are quite easy. But I will do, in any case, both of them later. Now I wish to look at the following observation. We wish to define that the x-axis is the line of real numbers, meaning that the number 8 is actually 860, and the number, I don't know, -2 minus 2 is -2 times 0. So if I go here, which real number did we mark on the plane?
3.
-3. I wish to say that the real numbers are these numbers here. Okay, that's what I wish to say. What could be the problem with me claiming it? But then we will get two different definitions for the operations. לכאורה. לכאורה, אנגלית? seemingly, זה לא נשמע טוב. seemingly, בסדר. I thought about it, but it's...
Apparently,
No, but it's not apparently, זה לא לכאורה. seemingly.
swimming, if you're swimming.
swimmingly, כן. seemingly, ככה. right? לכאורה. If I multiply 3 oh. If I multiply 3 by, I don't know, 2, what is the result?
Not in the complex.
6. No, in the real numbers,
Ah.
right? 3 times 2 is 6. Agreed?
Complex number.
But
zero.
wait, but if I claim that the x-axis, the real axis, it's called, is actually the real numbers, so 3 is actually the number 3 times 3 0, and 2 is actually the number 2 0, and then the multiplication have another definition, right? I know how to multiply these two by this definition, and I might get a different result. And then it doesn't matter when I told you I claim these are the real numbers if the operations are different. Luckily, it holds. It's the same thing. Look, what is 3 0 times 2 0?
2 times 3.
So it's 2 times 3, that's 6, minus 0 times 0, then 3 times 0 plus 0 times 2. That is exactly 6 0. And it also works with addition. So now I'm saying that the plane, it's called Gauss plane, Gauss's plane. The plane of complex numbers contains, therefore, the real numbers are contained within the complex numbers. It's just the real axis. The x-axis is called the real axis. It contains all of the real numbers, and the numbers which are not on this axis are complex numbers which are not real. Okay, yes.
Why don't we like, see how much is multiplying working with them or no?
Come again, I didn't understand.
We just saw how we sum them.
Yes.
Why don't we look how we multiply them?
We saw how we multiply them. We didn't see how we sum them.
Sorry.
And I saw it also
yeah.
works with addition because it's easy.
Sorry.
Yeah. Okay. So first of all, we enlarge the numbers we had. That's one main hurdle that we passed because we each time added numbers. So now I hopefully convinced you that we have the real numbers and then we have other numbers, which are the points which are not on the real axis. How do they behave? We will see in a short while. Now, define that I is the number. Who knows which complex number is I?
Square root.
That's not a definition.
Complex
The complex numbers are point on the plane. Which point is called I?
Oh, huh?
Which point on the plane is called I?
Everything else that isn't on.
No,
No,
it's
sorry,
just
0,
1 point.
0, 1.
0, 1. We define that the point 0, 1 is the 1 point we call I. The number I is that point. What are the properties of I? We will see in a bit. But that's the definition of I. I is the point 0, 1 in the complex plane, in Gauss's plane. Yes.
Can you use the complex thing to define the real numbers now?
Definitely.
Just,
The
like,
real
because
number.
We never
Yeah.
defined the real number.
And we
No. But okay, no, but it's a circular argument because we define the complex numbers using the real numbers.
Really?
right? We took the plane of two reals and the addition, so no.
Okay, so how do you
No,
define,
no,
how do
that's-
you find real numbers with
In calculus, and we won't do it as well. It's quite hard.
really?
Wait for Calc 5, bro.
No, you usually don't do it even on a math degree. Actually defining the real numbers correctly, it's quite hard. You just assume that it works. Okay, so define that, and now I can ask. Now we can calculate I squared. So what is I squared? It's I times I, which is 0, 1 times 0, 1. And what is that? Multiplication of the left ones, 0, minus the multiplication of the right ones. What do we get? 1. The multiplication of the outer ones is 0, plus the product of the inner ones. It's also 0. So what did we do? What did we get? Minus 1, 0. So which is called affectionately minus 1, right? It's on the real axis. Okay, so we proved that there exists such a number I, so that I squared is -1. So we build the number system, and we show that in this system we have all the real numbers with their operations, and we have an extra number which, when being squared, is equals -1. We didn't prove yet that this system is a field, but just because we didn't show the inverse, we will later on. But it is indeed a field. It does indeed contain the real numbers, and we've proven that there is a number such as p squared go exactly to -1 and 0, which is the real number -1. Yes.
It's a bit of an oversimplification. It should be I squared equals -1, 0. Right?
So yeah, but
Because-
I already said that the real axes are actually the real numbers, so I affectionately call them just by the left coordinate, right? But that is
but
the
technically the number -1 as the way you've written it doesn't exist
Yeah.
in the complex numbers. The
It-
number is -1,
it does
0.
exist, and technically when you decide to define that this equals just -1. It's just a matter of naming, and it's okay to name it that way. Okay? So it's more of a philosophical argument than a real one. Because one would claim that the real numbers are actually these real numbers. And anytime in your past when someone said -3, he meant this point. And it's not that far-fetched, because sometimes you draw the x-axis as an axis. So you might as well call it -3 plus comma 0. But it doesn't really matter.
The reason why I'm saying is just because if you, with the way that you write it, I squared equals -1, then like, you know, before you learn complex numbers, like you hear about this, oh, I is the root of -1,
Yeah.
but actually technically it isn't the root of -1, it's the root of like -1, 0.
So again,
which
so
makes
I
more
claim
sense as like,
no,
oh,
but
so
I
it's a
claim
completely
it
different
is
thing.
the root of -1, and you just didn't know it. You just didn't know that -1 is actually a point on a plane. Okay, now I'm
Okay,
telling
so
you,
let's
but
look at it
it's
the other way
a
around.
semantical, philosophical argument and not a mathematical. Mathematicians do argue about it,
Yeah.
but it doesn't really matter.
I like how you define it at first. It's a philosophical argument, not a real one.
Yeah, exactly, exactly. Okay. So now let's calculate, and now we're taking a huge step to the language which is used in high school for whoever saw it. That A plus B times I. Now, your question before I'm
Saying that I
continuing.
squared is -1, why aren't we defining I as a singular number?
What do you mean singular?
Just like you're defining it as a point. What,
Yeah, because the complex number, the system we built, every number in this system is a point on the plane, right? I said all of the points of the type a, comma, 0 are the real numbers. So -1 is actually -1, comma, 0. I took a pointer 0 plus 1, comma 1. I chose to call it I. You could call it J. It might as well. And then I proved that if you take 0.1 and multiply it by itself, you get to -1, comma 0. So there is such a point, such a number in this system that when being squared goes to -1. You might say, okay, this whole thing doesn't matter to me at all because these are not quantities I understand, so it's all meaningless. So for that, I will tell you two things. First of all, it's a great mathematical theory that has proven great results. That's one thing. And on the other hand, I will also try to convince you that it does measure some kind of quantity, that it actually makes sense even to define it as such. But for now, it's my right to define a new number system with a new type of addition, a new type of multiplication. And in that system, 0, 1 times 0, 1 is -1, 0. Do you agree about that? So that's it. That's all. That's what I claimed. I just affectionately called 0, 1 I and -1, 0, -1. Okay, but I did prove that the real axis acts with addition multiplication just like the real numbers. So it makes sense to say these are the real numbers, but I didn't explain who is I because it's a new number. It's not on the real axis. It's somewhere else on the plane. So now let's calculate a plus b times I, where a and b are real numbers.
This is supposed to be without parentheses, right?
What do you mean?
Like this is not a distribution. This is just like A is a real number and B.
Yeah, you'll see in a second.
Okay.
So what is a plus b times I? So the real number a, which point is it actually?
A0.
A0. And the real number b is b0. And the number I,
0.
1. Agreed? And now when we have it in the language with which we defined the complex numbers, we can calculate it. So first we do the multiplication. What is b0 times 0, 1? So left times left is 0, minus right times right is also 0, comma. The outer ones, which are the outer numbers here? B and 1, so it b times 1 plus the inner ones are 0. So we get a0 plus 0b. And what is a's 0 plus 0b?
A, B.
AB. So we've proven that a plus bi is just another representation of AB. And now we don't have to look at this horrible representation at all, and we will continue, we will stick with the A plus BI. And that's important because this is addition and this is multiplication between the B and the I, and we have the distribution law. And let's look at the following example. So AB times CD, we've defined it to be AC minus BD and AD plus BC, right? On the other hand, AB times CD. What can I write now instead of A comma B? A plus BI. What can I write instead of CD? AB, we said equals to A plus BI. CD, what does that equal? C plus BI, right? Wasn't a trick question. Okay? And now I can use distribution law. לפתוח סוגריים. What do I get?
AC minus D,
AC
minus VI,
plus ADI. Agreed so far? Plus BCI. And the last one?
BD,
BD.
II.
I squared. I. בדיוק. Okay, I squared. Agreed so far? That's the way they learn in high school. In high school, they show the complex numbers starting with saying I is the square root of -1, meaning I squared is -1. Believe me. And then a complex number is A plus BI. And then when we multiply two such numbers, they use the distribution law. Believe me that it works, right? You see why these properties are important. We use them. Okay, I also say, believe me, that it works, to be honest, but I gave you the tools to verify for yourselves. If we go to the distribution law, three complex numbers would be A, B, C, D, E, F. You can substitute them into this formula and verify, yeah, that the left-hand side of the equation equals the right-hand side of the equation. I'm not doing it because it's a waste of time, but when I define it properly and I define the multiplication and the addition, I can verify that it holds. So I define it well and say, believe me. I don't just say, believe me, without definition, which is slightly better. So when we use the distribution law, we get this. And now let's reorder the numbers a bit and look for the most part, notice for the most part, what is I squared? That's -1, that's -1. So that equals actually AC minus BD plus take I as a common factor, I times AD plus BC. And you can notice that that's that's the first reason for that weird, seemingly weird definition. Okay, you can assume that someone started with assuming that I is the square root of -1, and then he found out that that would what would happen when you multiply two complex numbers, you will get the real part is AC minus BD, and the imaginary part is AD plus BC. What I just told you, I will write definition. Given a complex number A plus BI, and from now on, I will write it as A plus BI. It's the same thing as AB. Let's call it Z. Then the real part of Z is A, and the imaginary part of Z is the B. Okay, the real axis and the imaginary axis. Okay, we use it sometimes. Do you have any question so far? So, and another example, and I wish to go to the example which I had before. We saw that 1, 2 times -3, 0 is -3 -6. Now let's see it in our new natural notation. So what is the complex number 1, 2? What complex number does it represent?
1 plus 2.
1 plus 2 times I. And we wish to multiply it by -3. Agreed? Look at how easy it is. So obviously it's -3, -6 minus 6 times I. Agreed? It's much easier in the new notation, right? I just used the old one to prove to you that the definition is the complex numbers are well defined, but for the day-to-day work, obviously the new notation is much better and simpler, right? -3 times 1, -3 times 2i. By the distribution law, you get -3 minus 6i. Agreed? Next, definition. Given a complex number z equals a plus bi, we define the complex conjugate d bar to be a minus bi. Let me just verify that I use the right word for in Hebrew it's the tzamud המורכב. I'm pretty sure it's conjugate, no?
Yeah.
Right? tzamud מורכב. Just verifying.
It's not complement.
No, I don't think so. Yes, complex conjugate. Okay, that wasn't mistaken. So if you have a number a plus bi, the conjugate is a minus bi. For instance, am I always in Italy? I'm pressing something that, okay. For instance, what will be the complex conjugate of 1 plus 2i? Not a trick question.
It's 1 minus 2.
1 minus 2i. And what will be the complex conjugate of 1 minus 3i? 1 plus 3i. Because the b is -3 and minus is a plus. What would be the conjugate of 4?
4.
4. Because the
There is no
imaginary part is 0. The b is 0 and -0 is 0.
It's really imaginary.
And lastly, what would be the conjugate of I itself? Minus I, because the b is 1 as it is. Okay, so this is the conjugate. One of the first thing when students who sees this for the first time is the natural question: why do we look at this weird definition? Why should I just take the minus of the imaginary part? What could it help me? And I will answer it in a bit, but for now it does look capricious. Why do I need to look at the conjugate? But it does have it has a lot to do with the inverse. That's why. But it's not clear at all now why. We'll see it in a few steps.
Is it because like when you multiply them together, you get positive part?
Yes, it's on the line of the inverse. We just need to fix the size. That's the inverse, and that's, I don't know, that's nature, right? That's the truth. That's the one that gets to one. So I don't have any. I have a few other explanations, but for now it seems totally capricious. Okay, so now we will now we will notice the following fact. If z is a plus bi, then z times the conjugate of z, the complex conjugate, is a plus bi times a minus bi. Agreed so far? So that's a squared minus bi squared.
So it's a
it's
square
B.
plus b.
Because I squared is -1, that equals a squared plus b squared. So now, what is z times the conjugate of z times 1 over a squared plus b squared? Remember, a and b are real numbers. So a squared plus b squared is a real number. It has an inverse because the real numbers has an inverse. When is the one time that you cannot divide by a squared plus b squared? When it's 0. But when does a squared plus b squared equal 0?
0, 0.
Only 0, 0, which is the 0 of the field. So every number other than 0 has an inverse, which we will see in a second, other than 0. That's fine.
Mhm.
So what do we get here?
1, 1.
Exactly. It's a squared plus b squared over a squared plus b squared, which is 1, which makes that formula the inverse of z. And we proved here the sixth property of a field. Every number other than 0 has an inverse number in the complex field. And that was the least obvious part, I would say. And we're right about the 0. This holds whenever a squared plus b squared is different than 0, meaning for every complex number other than 0, which is 0, 0. So the complex numbers are actually a field, and in this field there exist the real numbers and other numbers, one of them being squared equals to -1. So we're able to get our cause, so to find a field which contains the real numbers and has a square root of -1 in a sense. Questions? Well, so now see an example. Look at the following example. Let's look at the equation. 1 plus I z equals 2 minus 4i. So it looks frightening, but if it was real numbers instead of the complex number, you would say it's the easiest question in the world, right? If I told you, and I did it before with the modular field, right? If I have 2 times x equals, I don't know, 8. So we say, that's easy, I'll divide by 2, x equals 4, agreed? But it's supposed to work on any field because division is multiplying by the inverse. The reason it's hard for us is that we are not familiar or used to finding the inverse in the complex numbers, but we have it in a formula even, right? So you don't need to memorize the formula. We'll give you a shorthand in a bit, but this is actually quite an easy question. So what you need to remember, what was the inverse? The inverse was the conjugate, and we divided by a squared and b squared. So you don't need to remember the a squared and b squared, just the conjugate. Multiply by the conjugate. We will multiply both sides of the equation with the conjugate of the coefficient of the variable z. So what is the conjugate of the coefficient of z?
1 minus.
1 minus I, exactly. I.e. 1 minus I. And let's see what do we get. So 1 minus I times 1 plus I times z equals 1 minus I times 2 minus 4i. Great. So on the left hand side, 1 minus I times 1 plus I is actually, how much is that?
1 minus.
No,
No,
no, no, it's so
2.
yeah.
yeah.
Why? Because I will do it for the first time, I will do it slower. 1 squared minus I squared z. But I squared is plus 1. That's the a squared plus b squared actually. So we get 2z. And on the other hand, we need to use the distribution law. So 1 times 2 is 2. 1 times negative 4 is 4i, and minus 2i plus 4i squared. That's a bit like this. And now here on the left hand side is 2z. On the right hand side, we get 2 minus 4 is negative 2. This is minus 4. Minus 6 times I, 6i. And now, so what is z?
-1 minus 3.
-1 minus 3i. And we were able to solve this equation over the complex numbers. And we go to Wolfram Alpha, which is very helpful. And we paste the equation, and hopefully it will give us, and it did, the very same answer. Okay, we were able to solve an equation. Later, we will need to be able to solve a system of equations with few variables, but that is the main part here, to understand that instead of dividing, we multiply by the inverse. And I wish to show you, I will show you the way they do it in Israeli high school.
No.
What's the problem then? Not one word? I don't know. In high school, which is parallel. It's basically the same, but some students find it like different. I don't know, but I wish to show you. And again, whoever never seen it before, it doesn't really matter for them, but maybe they will like the other way to see it. So how will I solve it in Israeli high school? So first of all, I will divide directly by 1 plus I, which is quite intuitive. Then I get Z equals 2 minus 4I over 1 plus I. Agreed so far? Which is true, but this fraction, I don't like it because again, I have a complex number in the denominator and I don't know what to do with it. So the next step that the teacher will tell you to do, multiply both the numerator and the denominator of this fraction by the conjugate of the denominator, which again, it's virtually the same thing to do. Okay, so the next step we say, okay, so Z equals this times 1 minus I over 1 minus I. Then you will get here on the top minus 2 minus 6I because we calculated it before over 2, which obviously give us the same answer and basically even the same calculation. The upside of this method, so-called, is that you need to remember even less because you divide. But still, you need to remember to multiply by the conjugate. There is no other way to do it other than multiply by the conjugate. So I multiplied it both sides by the conjugate, and they multiplied numerator and denominator. But in any case, we multiplied it twice by the complex conjugate in order to find the result. Any questions so far? So this was the algebraic window into the complex numbers. And next week we will see a geometric one. Afterward, we'll do matrices and linear equations and whatnot.
All the fun parts.
Everything is fun with me. I'll see you at 4 o'clock. Bye-bye.
Bye.
Whoever is in calculus anyway.
We got like 2 hours. Let's go.
Yeah.
Oh, let's go.